And so Samir doesn't require any introduction now. All of you are learning with him and in a very effective manner. That is what I can make it out from the chat. So I will not take much time. Samir, you can please.
Yeah, yeah. Thank you so much for
So today we have
so
done this segmentation thing, and Samir will take you with that.
yeah, yeah. Thank you so much, ma'am. Yeah. So I welcome everyone, and again this day, that is I think day 8 for this lab session. So let me share my screen first. Yeah. So again, I'll ask everyone to go to this Google Drive where I've shared the data related to today's lab session. So that Google Drive, which is shared with you, the folder that is shared with you. So I'm going to that one. So this is the folder, and this is day 8. Yeah. So the data, the name doesn't suggest what data I have taken. So let me tell you. Just go to the Kaggle, and in the Kaggle you will have a CVC clinic dataset, CVC clinic DB. So what is this dataset all about? So there is a procedure that is known as colonoscopy. Okay, so in colonoscopy, we use it is used for the investigation of GI tract, and in colonoscopy we used to record video sequence through an apparatus that has a camera and a flash module. So through that the video is recorded, and then the images are taken out. So colonic polyps, polyp is a kind of disease, or there's a lump of cells. Okay, so I'll tell you what is polyp. So polyp is actually a lump that is going out. There is an abnormal growth, and that forms on the lining of colon. So that is why the colonoscopy is used. So the most important thing with the polyp is since I am doing my research in capsule endoscopy images. So since in capsule endoscopy, GI tract is investigated, gastrointestinal tract is investigated. So in colonoscopy also we used to investigate, but the problem is that the procedure is different for endoscopy and colonoscopy. Okay, so for colon polyps, we use colonoscopy to get the details about them. So for the treatment of those polyps, um, first we have to find the outer lining of those polyps, like what is the extent of that polyp that is present inside the patient, and for treating those polyps we have to remove them. So a doctor needs to remove them through a surgery. So segmentation of polyps is a very important thing, and it is very popular when people are doing research on GI diseases. So today we have taken a data set that is related to colonoscopy, where we are having images that contain polyps. So this is an open source data set, and it is around about 137 MB. Since this data set, when it was released, the images were of TIFF format, but in Kaggle, this person Balraj Ashwath had given us the images in the form of PNG. So we don't have to convert these images from TIFF to PNG. So they are directly given. So instead of downloading directly from here, I'll ask everyone to take directly the PNG images that I've put in this folder that is inside this day 8 lab session. So I think everyone have got this thing. Now we will again, I'll ask you again to open your Google Drive. So this is the shared folder. So open the Google Drive again, and what you have to do, create a new folder. So I'm creating a new folder for today's lab session. Okay, so I'm writing day 8, day 8. So AI/ML. So why I don't know why today the drive is working very slowly. So AI/ML day 8 lab. So this is the folder that I've created right now. Okay. Now what I will do is I will create a new collaboratory notebook, Google Colab notebook. So first what I will do, yeah. So I think everyone is with me right now, where we are having three things. One is my drive folder, AI/ML day 8. This is my drive folder, the Python notebook, that is a Jupyter notebook given by Colab, and the third one is day 8 lab session. Yeah. So I'll give you the link is there, like, for this data set. So let me. This is the.
It is the same place from where you are getting things earlier. I think this staff has shared you in the first session. The
Yes,
same
yes.
which you are following. Yeah.
Same link, ma'am. Yes. Yes.
Okay.
Okay, so we are having three things right now. There is one folder that is AI/ML Day 8 Lab. This is my folder, my own folder. This is the collaboratory notebook, and then this is the folder where we have shared you this png.zip. That is our data set right now. So it is a file right now, and we will extract the contents of this file to have a data set in our own folder. So what has to be done is the same that we did in the last yesterday's lab. So first I'll rename this notebook. So polyp segmentation. Polyp segmentation is the name of this notebook. So AI/ML polyp segmentation. Yeah. So this is the notebook that we have created. So first thing is that you need a data set. So we will extract the data set. Okay. So first thing is you have to mount. So first it will connect and then it will mount the drive. Okay. So it is showing connecting right now here, and it is initializing. Yeah. Okay. So first thing is you have to mount this. So I'm mounting this. Yeah. Connect to the Google Drive. So it is connected right now. So let's start the session today with the first code that is on unzipping the file. So first we have to import zip file. Okay, import zip file. Now source from where we have to take the zipped file. So source zip equals to my drive. And first thing is you have to create a shortcuts first. So I will create a shortcut. So add a shortcut to drive. So everybody has to do that. So from here, this will be the same thing, and wherever you want to add the shortcut. So my drive, I'm going to my drive where I have AI/ML day 8 and I have added a shortcut. Yeah, so this is the shortcut that I have created. So day 8 lab session, there is a shortcut for png.zip. Okay, so yeah, this is the shortcut. So I'll close this folder right now, tab. Now there is no need for that tab. Yeah. So there's a shortcut in this drive. Now what I will do, I'll go to this thing AI/ML day 8 lab png.zip, and now I will copy the path. So this is the zipped file. Now destination. So what will be the destination? So it's the same folder, I think. So we'll copy the path of this same folder. That is AI/ML day 8 lab. Okay. Now what we will do, we'll
Hello,
extract.
Samir.
Yes, ma'am.
I mean, go a bit. Uh, be slow. Just take care that everybody is following.
Yes, ma'am. Yes, ma'am. Yes, ma'am. Yeah.
Oh.
Okay, so I was a little bit fast with this thing because I have already told you yesterday. I'll wait for you to create this thing. So the code I will share this code with you. So dot zip file. Now source zip. So where we have to take this thing. So zip, in the read mode we have to do this as zip, and then we have to extract. So zip dot extract, and all contents we have to extract. Destination folder. So I'll run this thing and I'll wait for you all to do this task. Please let me know. So in the chat, please type extracted. So just type extracted if you are done with me. So I'm waiting for your responses. Okay. Yeah, good. So many of you have done this thing. So let us check whether this is present or not. So PNG folder is created right now. Now, second thing is that let me share this code again. So this is the code. Now we have a folder that contains PNG images. So this is the actually it contains two. So actually Google Drive takes some time. So I will show you from here. So it contains, this PNG is a data set that contains two files, ground truth, and two folders, ground truth and original. Okay. So ground truth is something that is mask, actually mask. Okay. Original is the folder that contains images. So it contains images with corresponding masks. Like for particular this image, this is the mask. Okay. So let's check it out. What are there? So I'll ask everyone to rename this ground truth because there is one space in this in the name. So I'll rename this actually. So rename folder, and I make it either ground truth or GT. You can directly type GT. So let us refresh this again. So there is GT folder and original. Ground truth I have renamed it. Okay. So I think you have renamed it. So please type renamed. Okay. Yeah. So there are two things, original and ground truth. Now let us count how many number of files are there. So for that there is a command, wc minus l is a Linux command from which we can count what are the number of files present over there. So I'll copy this type ls. So if I'll type ls and then give the path, then what it will do, it will just display the names of all the files. I don't want the names but the count. So I'll put this thing wc space hyphen l and then run this thing and see what is the output. So there are 612 files in GT folder. Okay, so how many files are there? 612. So I think in your case also there are 612 files in ground truth. So I'll copy this. And let us check with the original also. So copy path ls wc minus. See what happened. There are only 598 files. Okay. So this is the issue with whenever you extract these files in Google Drive, there is some latency and there may be some problem, like what file is there, what is not there. That is why I was asking. So again, we have to unzip and then we have to make it clear that how many files, what are the names of those files. They should be equal. Okay. So again, I have to do the same thing. It is a big problem. Or second thing is no. Mm, or you can do one thing. Um, you can directly download and upload this. So let me do this again. So yeah, so there's one problem with this. GT is there. Again, let me check if there is some updation or there are 598 files. There 598 files are there. So let us do one more thing. Let me rename this as old PNG, like re rename it as the old one. So PNG old. Again, I'm going to unzip this. Okay. So let us unzip it again. Okay. So if you are getting 612 for both, that is all right from your side. Yeah. So there's some problem in my Google Drive right now. Let me check again whether there are you know same number of files or not. So let me check with the folder. So yeah, PNG, and then refresh this folder. I have to refresh this folder. So PNGs has not been created right now. There's some problem. Yeah, so it is not creating. Let's wait for 1 or 2 minutes, or I'll upload this. I'm also having the same thing in one of my folder, in this folder. So I'll refer to this folder only. Dataset and this PNG. So GT is there and then original is there. Yeah. So let us see if there is some updation or not. Yeah, PNG is there in my file. So I can check it out over here. Yeah, PNG is there. Okay. Let me check it again. Like how many files? Okay, it is saying no such file. no such folder or file. Okay, so let me take the paths of this thing. Okay, GT it is saying. Okay, sorry. So I have to convert the name, like rename it. So it is GT right now. Let me refresh it. Yeah. So let us check it again. 612. What about original? 612. Now this is correct. So I'll ask Neha ma'am or Durgesh to help Mr. Law Kumar Singh to get the link of this YouTube session. Okay. So now we are, now we have seen that there are 612 files in just this ground truth folder and this original folder. So let us uh, print one of these files and mask so that we will be able to understand where is the polyp and how we can relate this thing. So PNG folder is actually it is of no use. So I'll delete this folder so that there is no confusion. Okay. So PNG I will delete. Yeah. So this is of no need right now. Okay, PNG we need. So don't worry about PNG old. There is it has no use. Okay, so just focus on this folder PNG ground truth and original. Now let's start. Okay, so first thing that we need to see is what are the images. What kind of images are there? So this is the for ground truth path. So GT underscore path. This is the ground truth path and this is the image path. So img path is this path. Okay. So I need GPU. Yeah, we need GPU. Thank you for telling me again because we have to see. Let me check. Yeah. So we need actually invalid syntax. Okay. So very well asked by Mr. Rohan. So we have to check. So it is none. Please make it GPU runtime. So make it GPU. Today we have to use GPU. Thank you so much, Rohan, for telling me. Yeah. So make it GPU again. We have to perform the. We have to check like what is the runtime. Okay. So drive will be actually added again, but this folder that we have extracted earlier, it will be same. So there is no need to run these codes. Okay. So let us check. Yeah, it is connecting. Yeah. Okay. Now, so let us do one thing. Uh, let us check. Yeah, drive is there. My drive is there. Now I have to check day 8. So yeah, AI&ML day 8 is there. PNG is there. Okay. Yeah. So all correct. Okay. So I'll set the ground truth path and IMG path, image path. Okay, for these two things. So again, I'm telling you, for in this PNG folder there is a ground truth folder and there is a image folder. So we have copied the path, like for copy path and make it ground truth path. So this is ground truth path and copy this path from original and make it original image path. Okay. So this is image path and please click on this play button. So I think you are with me right now. So path set, I think you have set the path. So path set. You can type like this path set. So we will speed up with this thing. Now, yeah. What about others? Have you set the path? Yeah, thank you so much. Okay, so now first we will import matplotlib, or we can use okay, matplotlib. So using PLT, we can plot the image. Okay, so why I am importing this matplotlib? To plot the image. Okay, so PLT, so test img is plt dot imread and the image. So what is the image that I want to check is first the original image. Okay, the image which contains polyps. So one.png, I'll copy the path, paste it over here, and plt.imshow and test underscore img. So this is the image that contains polyp over here. So this is polyp. You can see the growing structures on the lining of this colon. So this is colon, and here this is polyp. So polyps are very, vulnerable when when they become cancerous. So we have to segment these polyps so that a surgeon can get help, that what is the boundary of that polyp and how serious it is. So let us check what is the dimension of this image. So PLT, sorry. So our test IMG, so test underscore IMG dot shape, we will type. Okay, so the shape of this image is 288 cross 384 cross 3. So it is a RGB image because it is a colored image. So three channels are there, and the number of rows is 288 and number of columns is 384. Okay. Now, you can do this for the mask also. So this GT also, ground truth also, for the same image. So we can get the lining of this particular segment. So we'll come to know. So I'm again copying this code, pasting it over here. Now test GT. I'll make it GT, ground truth. And instead of original, I have to go to ground truth. So this is GT and test GT. So this is, yeah. So here you can see that for this image, this is the corresponding mask. Okay, and this is the polyp region that is highlighted in this mask. Okay. Now we will test the mask also. So test underscore GT dot shape. So here you can see that the mask is although it is a binary mask. Binary mask means there are two kinds of pixels. So here you can see visually there are two kinds of pixel, a white pixel and a black pixel. So this is a binary mask. But when you are plotting this mask, you are having three channels. So actually this test GT is same in all the three channels. So if you will take the first channel, how you will take the first channel? All rows, comma, all columns, comma, 0 is the red channel. So when you will see this red channel, it is something, comma, C map equal to gray. So when you will take gray as C map, you will see that it is same like this. Okay. So for 0 also, so this 0 means R channel. Okay. 1 means green channel. Okay. So again for green also it is same, and 2 is blue channel. So it is also same. So either of them we can take. So we will prefer red channel. Okay. So to convert it into a single channel image. Single channel means in this image there are three channels, but we need a single channel image. So how we can do that? We can directly take this thing. So this will be a single channel image. So so there will be, so when you will print the shape of this dot shape, so you'll get only one channel, like 288 cross 384. Only one channel is there. Okay, so this is a grayscale image right now, and these are RGB images. So what we will do, we will create a CNN that will contain an encoder or decoder, and decoder will encode this whole encoder decoder architecture will predict a mask. So what it will produce? It will produce a mask. That mask will probably show the polyp regions. Okay, so this is the task for today's lab. So how to do that? So first is we have to create the training and validation data set. Okay, so we can do this by splitting folders, either splitting folders, or we can directly read the images and X test and Y test, and then we'll do like that. So let's do that. So first thing is, first we will read all the images. So for reading all the images, you have to create, we will create a function, and here we will use CV2. So why CV? Because Open CV will help you in reshaping. Like if we want to change the size of this image, so you want to resize that image, then it will help you in like making it a lower dimensional image or higher dimensional image. So let us see OpenCV2 also today. So first thing is that we have to prepare the data set. So let me type this here. Let us prepare a data set. So I think you are with me right now. Yes or no? Is there any problem? What about others? Are you there with me? Okay. Yeah. Good. So let us prepare the data set. So for training, we need X train, Y train, and all that. So first we will prepare a data set that contains X. What is this X? X is the training data set of X is the data set of training images, training and testing images. Okay, and Y will contain the corresponding ground truths. Okay, so how we will do that? So let us create a function. So first we will import CV2. Okay, now um, we'll create a function. We will
Samir,
define a
please,
function.
Samir,
Yeah,
somebody
ma'am.
is asking, please repeat. Sham Deshmukh ji is asking.
Yeah,
Can you
ma'am.
please repeat the last step? Yeah.
Which way will be
Just
perfect?
read it out. Thank
Okay, okay, yeah. So what we have done till now is we have extracted this zipped file that was shared with you in the shared drive that you already have. So from there we have copied that folder. We have created a shortcut, and
Hello.
then
Hello.
yeah,
Sorry to disturb you, sir.
yeah.
I just wanted to know what are the steps which we will be following. You just mentioned few steps which we'll be doing in this assignments. So those like preparing a data set, afterwards segment, something encoding and decoding like that.
Okay, I'll keep on writing here. Okay, in this
Okay, no
whole
problem.
notebook.
No,
Yeah.
no
So
problem.
you'll
Thank
be
you.
able to catch up like what is there.
Yes, yes, yes. Yeah, you summarized few steps, so I thought that like it will be.
Okay, okay, okay.
Yes, yes. Thank you, sir.
Yeah. Okay, so we will be we'll now create the data set. So that create data set. So creation of data set, we will take both the path of these ground truths and path of these images. Okay. So we have already defined the path. Okay. So this is GT path and this is image path. Okay. So I'm pasting it over here so that there is no We don't have to move there. So yeah, so we'll pass two paths, like image path and GT path to this function. Okay. So for this, we will be reading one image at a time. Okay, and then we will be adding that image to a list. So we have created a new list here, x equal to this empty list and y equals to this empty list. So what we will do, we will be reading one image at a time, and then we will be adding that image to this list, empty list, and then what will happen? It will get populated. Like we will add and one image at a time, and then this email, this list will be growing larger, and all the images will be in this list. So this is for the polyp images, and this list is for the ground truths. Okay. Now, so to read the polyp images, we will write a loop. So for file name in os dot list dir. So we need os. So we have to import os also. So import os. So for file name in os dot list dir. Now we will pass the image path. Okay. And for ground truth, what we have to do is we have to write a loop for GT. Okay, so GT path, ground truth path. Okay. Now, so there will be two for loops. One for images, the polyp images, and the second for ground truths. Okay. Now, what we have to do first, one more thing will come back, and I'll tell you later. Okay. So one thing is img equals to cv2.im read. So we will use cv2 right now. So cv2.im read, and cv2 will help us in reading that image. So image path plus file name. So when we are giving this image path, please check it out whether there is a forward slash there or not. Otherwise, it will not get inside this GT folder or this original folder. So it will be outside that folder. So we have to add this thing. So I am again running this cell. Okay. So GT image path is plus file name. So this is image. Now this CV2 actually, suppose I'm using this CV2 like here. So like I'm writing import CV2 and I'm writing cv2.im read this particular image. So this is test img equals to cv2.im read, and then I'm plotting this image. So cv2.im show, actually cv2.im show does not work in collab. So let us do that, and then we will check it out what is the error, and from that error you will be able to learn. So name cv is not defined. Okay, so cv2, yeah. So it says, like collab says that cv2.im show is not supported here, because cv2, when you will use cv2.im show, a new window will be generated. So in case of Google Collaboratory, that we are using a browser. So in a browser, there is no aid for creating a new window. So they have helped us in Collaboratory that you have to import this thing. So first I'll import this thing, and then we will rename, like we will use this as this cv2 underscore im show. So when I've taken this, so this is the cv2. Okay, but what happens is cv2 always reads the image in the form of bgr format, like first blue, then green, then red. So whenever we use CV2, we have to convert the image from BGR to RGB. From BGR to RGB. Since we have read this image from CV2 and then showing this image from CV2, it appears to be same like that. If it would have been like we have read that image using matplotlib and then printing it using CV2, then there would have been another kind of image, like it should be a blue in, like more in blue color. So yeah, so I don't know how to share collab live link. So share is there. But it will, okay, copy I'll take, and this is restricted. Okay. So I'll share this to everyone. So this is my notebooks actually link. Okay. Yeah. So here what we will do, if we are reading image from CV2, we have to convert it from BGR, that is blue channel, green channel, R channel, BGR to RGB. Okay. How we will do that? So IMG equals to CV2 dot CVT color. CVT color is the function, CVT color. Okay. And then we will pass this image and we will type CV2 dot BGR to RGB. Color, let's go BGR to RGB. This is the function that we have to add whenever we are reading the image from in using CV2. Okay. So BGR to RGB. Now, since this image, since we are reading it using CV2, so when you are reading an image with CV2, the image is in the range of 0 to 255. Let us see. So this image is test IMG that we have read from using CV2. Let us check it out. So test IMG, first we have to import NumPy. So import NumPy as NP, and then we will type np.unique test img. Okay. So there are pixel values from 0 to 255. So when we are creating the data set, here we are creating the data set. So when we are creating the data set, we have to convert these images to 0 to 1, between 0 to 1. So how we will do that? We will divide this image with 255. So IMG equals to IMG divided by 255.0. Okay. So we have divided this image from 255. So what is the maximum value? Is 255. Yeah, access is denied because if I'll give you the access, you will be able to change this collaboratory notebook. So there is one comment somebody have asked that access is denied. So otherwise, there is if like mistakenly you have deleted some line, then there will be a problem for me. Okay. So keep on writing the code with me. I'll share this code when it will be fully made. So I'll share it with you. So IMG equals to IMG dot 255.0. Okay. Now what you have to do, this is the image that you have taken out from the folder, from this folder, original folder. Now what you have to do is you have to add this image to this X. How you can do that? So X dot append, and then you can pass this image IMG. Okay. So X dot append IMG. So it will be appended to this list. Okay. Now now what we have done, we have not, like, what is the shape of this image? So we have seen that the shape of image is 288 cross 384 cross 3. Okay. Now if we want to resize this image, okay, resize this image, like we have to shorten the image. I want that image should be image should be 244 cross 244. Okay. So times 244. And original image is of what size? 288 cos 384. So how we will do that? So for that, we can use cv2.resize. cv2.resize. How we will do that? So let's do img.cv2.resize, and then we will pass this original image img that we have converted into. We will convert this image later on to floating point. Okay, so we will keep this before this 255.0. Okay, so img, and now what is the size? So I need it like 224 cross 224. Oh, sorry. So I needed 224. 224 is in many cases pre-trained models, they use 224 as image size, so that I have taken it for me, my size, for this case also. Now, interpolation. Interpolation is like what if the image is upscaled or downscaled. So how the pixel should be replaced. Like if we are downsampling the image to 1/4, so 4 pixels will be represented by 1 pixel. So that will be 1/4. If suppose you are if you are making it bigger, like expanding that image, so for that if you are making it double, okay, so in that case also some of the empty places should be filled by some pixels. So interpolation is needed for that. So let us do interpolation equals to cv2 dot linear interpolation. Okay, so this is linear interpolation that we will do. So this code for reading the images from the reading the polyp images is done. Now we will go for the ground truth. Okay, so pre-processing is very important part that we have to add. Okay, whenever you are writing a code. So now for this ground truth, we are coming back to the ground truth here. So this is test GT. Okay, so this ground truth we have seen, and when we will read this using like cv2, and then when we will plot it using cv2. Okay, so let us see what is, since it is reflecting in only 2 colors, so this is a binary mask. But let us check what are the actual pixel values in this mask. So for that, we will write np.unique, and then this test underscore gt. Yeah, you can do also polynomial interpolation. Yeah. So here, not polynomial, but there are many kind of interpolation techniques you can see in cv2. So like nearest interpolation is there, so whichever pixel is nearest. So not like that, like it cannot be related to like svm polynomial and svm linear, not like that. Okay, so here you can see that here as this mask appears to be only in 2 color, but here you can see that not there are more than 2 pixel values. So we have to convert this mask into a binary mask. Binary mask means we have to convert this mask such that there will be only 2 pixel values, either 0 or 255. And when this image is converted into a floating point image, you will divide it by 255. So there will be values from 0 to, there will be 2 values, 0 and 1. So directly we will convert this 0 and in the form of 0 and 1. How we can do that? So if I'll write a code like new test gt equals to np dot where there are values that are greater than, so between 0 to 255 there are values. So the values when test GT is greater than, we will take a middle value. So 127 is the middle value. So whatever pixels that are greater than 127, please make them 1. The pixels that are less than 127, please make them 255 and please make them 0. So which are greater than 127, make them 255. Which are less than 127, please make them 0. So in this way, and using np dot where, we can convert this mask into a binary mask. So this is what we have made the pixels greater than greater than 127 as as 255 and less than 127 as 0. Okay. So now we will print this thing. So let us print this thing. So CV2 IM show and this new test GT. So here you can see that this is now a binary mask, because when you will check the values inside this mask, so there will be only two values, 0 and 255. So we have converted this mask from 0 to 255 to a mask which has only two values, 0 and 255. Have you got it? Is it okay for you all? Have you understood this thing? This is very important part when you are doing something on medical imaging, or like you are segmenting the image in two parts, like two binary segmentation problem is there. Yeah. Okay. Yeah. So let us come back. So this operation that we have written over here, this needs to be added when we are creating the data set. So how we will use this thing? Okay. So first we will read the image. So I am copying this code same as it is. So img cv2.im read, and now here GT path is there. So ground truth path. Okay. And image is same, or you can, for making it easier to read, make it GT equals to. Now GT equals to np dot where GT is greater than 127. Now since we are dividing it to 55.0, so we will make it like that. So np dot where GT is greater than 127, make it 255 or 0. Now GT equals to GT divided by 255.0, make it 0.0, because we have to convert this as a floating point image. So what this is automatic typecasting that is going on right now here. So this is floating point. So this is integer value. So integer divided by floating point is floating point. So this is how we can do, and then add this to y. So y dot append this GT. Okay. Now you have to run this cell. So I'm copying this code. So new test GT Rohan was actually for this only, for the testing purpose. We have used new test GT. Right now, because we are reading the file in this GT variable, so that is why we don't have to write new test GT. Okay. So we are updating like GT over GT. So every time in each line GT is updated. So finally we get this GT. That is a floating point image, and that is a binary mask and all that. Have you got it, Rohan? Yeah. Okay. Okay. So for conversion of ground truth to binary, so Chitra madam, how we can do that is, suppose we are having these range of values in a mask. So I've already told you that the data set by default, it contains these kind of masks, and these masks are not binary masks. So these are 3-channel masks. Okay. Now, what we have done is we have taken a threshold. Threshold value is a middle value. Okay. So from 0 to 255, the middle value we can take it like 127. Okay. So the pixel values that are greater than 127, should be made as 255, and the pixel values that are less than 127 should be made 0. So there are only two pixel values, 0 and 255. So if x is greater than, x is some x is the pixel value, so x is less than 127, make it 0. If x is greater than 127, make it 255. In this way, this is a function. Okay. So yeah, np.unique, some Leeladharji, np.unique is actually what what are the values that are present over all over this mask. So it will not print like 9 twice. So only unique values, what are the values that are present over there, one time it will print only. So the uniqueness test is there. What are the unique values that are there? So if there are values like 20 is not there, 20 is not there, so it will not print because it is not present over this image. So unique values that are there, but it will not print. Like if it is coming more than one, it will not print it again. So uniquely it will print. So I think it is you have understood this. Yeah, so you are getting float values because you have not converted this, you have not read this with CV2. If you are reading the image with CV2, it should be converted, it will be in 0 to 255. If you are reading these images using matplotlib, it will be from 0 to 1. So matplotlib gives you the values in floating point, the images in floating point, and the other library CV2 will give you between 0 to 255. Okay. So this is the way we have got now. So okay, so if you are reading the image with the CV2, the image will be in the range from 0 to 255. So we have to divide it with 255 so that the image will be in the range 0 to 1. Okay, Shyamji, have you got it? What I'm saying? If you have
Yes, sir. Yes, sir.
that,
Yes, sir.
yeah. Okay, so we will proceed with by calling this function. So we already have this GT path and IMG path. So create. Now one more thing is you have to return this x and y. So return x comma y, or before returning it, before returning x and y, we have to convert them into a array. So what we can do, x equals to np dot array x comma s type. We can sorry, comma d type, and will be float. So after converting this array, this was list earlier. So x was a list before this line. Before this line, the x was a list. Now we are converting it into an array. So again, y equals to np dot array y comma d type equals to float. Now one more thing is there that we actually forgot to do is, since we need this mask to be of only like it should not have 3 channels. So we can do this like gt equals to gt all rows all columns and first channel we will take. So I think it is done. Now we will call this function. So this function is created. This dev create dataset function is now created, and now we will call this function. So how we will call this function? X comma y equals to create dataset and these two things like gt path. So first is image path and then gt path. So I'll, because I have taken the same name over here, I can directly pass them here. Has no attribute cv2. Okay, img equals to cv2 dot size. Yeah. It is saying why it is in which gt path it is saying. Okay, let us do one thing. So since there is, we will not convert it into a color, and some problems are there which like you may have, or there is no surety, like um, sometimes in collaboratory or somewhere like in cv2, so there may be a corrupted file. So due to that, there might be a problem. So what I've done is only I have read the image, because this is not ground truth mask is not a color image. So I have not converted into BGR to RGB and all that. So I've taken only one channel from that, then I've converted it, and then this is what we can see right now. Okay, so let us test the first thing. So um, x0 is what? So x0 dot x dot shape we'll see. So there are 498 images of 224 cross 224 cross 3. So we have converted it to 224 cross 224. Oh, I have written, yeah. Now, what about y? So y dot shape is, it is saying only 498 images it has read. Earlier we have seen there were how many images? There were 612 images. Okay. Why it is saying 498? Let us check it out. Yeah, so GT and original. So this GT path I'll copy, and this original path okay. Let us see this original path. Okay. So how many images are there? Oh, it is saying 498. Hmm. Oh, please give me another minute. So I'll take another path for that. So I already have this thing. mm, yeah, date. So this is the data set that I already have in PNG and this original. So I'll take the path of this thing and let us see. So this is the path for GT. No issues. I have a backup for that. GT slash, and for original, this is original. Okay. Yeah. So image path. It is saying some. Okay, let me check it out. Okay, there's some problem with this original slash. Uh, mm, on for which file? Let us check it for access 498 and y612. Yeah. Yeah. Hmm. Let us check it out. For which image it is doing so? Uh, what can I do? I have to think upon that. So this AI/ML PNG. Okay, let me do one more thing. Destination folder, I'll make final. Let me do this. So yeah, final is there. Now in final there is GT, so I'll rename it GT, make it GT. Yeah. So for this GT, I'll copy the path and I'll check it out how many files are there. Yeah, 612 are there. And what about this original six one two are there. Okay, no issues. Now what I will do is I'll copy this to original. Uh, this to original and this to GT. Okay, so GT is there. So this GT slash yeah yeah. Now it is done 612. Yeah, now 612. Okay. So there was some issue, I think. I don't know. Sometimes collab is very slow and some values doesn't get updated. So it is not always, you cannot fully rely on it. Yeah. Now we are having this. So X and Y. Now we will split this data set using sklearn that I have already told you earlier. So from sklearn dot model selection. Here, there is one library, test train split. So test train split. Okay. So from sklearn dot model selection, test train from sklearn test train split. Okay, train test is there. Yeah, this is train test split. Yeah. Okay. So we will split our data set into X train, comma X test, comma Y train, Y test. Okay, using this X and Y. So we will use this test train split, train test split. Sorry. So this is train test split. Now in this we will pass S X that we have already created earlier here. This X, this Y. Then we will give some random like test size. We will take it like 0.2. So 80% data we are having. We are taking for training. Okay, and then a random variable we have to set to. So random state, I think state equals to um, any number 31. So let us do that. Yeah. So now our data is set. We are having training data. So X train dot shape, we will see that yeah, X train has 489 files and Y train should also have these 489 files. So 489, 489, okay. And X test, we are having 123 files, and Y test, we are also having 123 files. So test train split done from your side. You can type test train split done. Then we'll proceed and we'll now make a model. So I'm very sorry today it is getting late. Yeah, some problem is there with OpenCV. Today I think because in the morning also Google Drive was not doing correctly working. So I did have in the morning this kind of glitch. So again, Rohan, I'll ask you to again unzip that file and then pass it to this function and do it again. So there will be no problem. Yeah. Okay. So I'm very sorry that we are so late, but still we will make a we'll uh, you know we'll do it in time. Yeah. So let us make a model. So we are having train test data set. Now I'm going to create the model. So for creation of model, we need Keras. Okay. So we'll start it from Keras, TensorFlow Keras, and then we'll add some layers and we'll make a encoder decoder model. So let's start. So import TensorFlow as TF, import TensorFlow dot Keras dot layers from Tensor. Okay, what we'll do from TensorFlow dot Keras import layers. We will import the layers only. So import layers. So whatever layers we will be we will need, we will directly add them. Okay. So how our model will look like? Okay. So there in this model we will be having an input layer. So there will be input layer. Second, there will be an encoder that will down samples and learns features. And what is decoder? Decoder will upsample the input from encoder and upsamples. Okay, so we will have one input, encoder and decoder. So we will try to define inputs. So inputs equals to input layer we will take. So layers dot input, and then shape equals to, we already know that we have reshaped this to 224 cross 224 cross 3. So every time a single image will be passed. So what will be the shape is 224 cross 224 cross 3. This is what is the input shape. Now we will begin with the functional API. So today we will implement the model using functional API. So using functional API, I'll tell you. Okay. So how we can do that? So we can define a layer like conv1 is the name of that layer, is a variable of a convolution layer. So layers dot convolution con2d, sorry, con2d. So I'm directly writing that how many filters will be there. So initial layers have a lower number of filters. So I'll take it 32. We know that the size of kernel is 3 cross 3. I'm adding a padding equal to same parameter. Padding equal to same means that whatever is the input will be the output. Okay. So that input image will not get downsampled right now. We will do the downsampling using max pooling operation. Okay. So this is what is one layer defined. Okay. Now what is the input to this layer? Input to this layer is this layer. So we will write like this: inputs. So this is functional API. We will define like this. We already know that convolution, after convolution, we use batch normalization and activation max pooling. So we will do like this. So in this model, in this segmentation model, we will first take two convolution layers, one after another. Okay. So there will be a pair of convolution layers. So con1, right, con1 over here. So this con1 is actually this con1, and now again this is a new con1. Okay, so there are two layers, convolution layers. Now this con1 will be given to batch normalization. So con1 equals to layers dot batch normalization, and what is the input to this batch normalization is con1. So this actually relates to the last con1. So this con1, okay. So like this diagonally, like this con1 is this con1, this is this. Now the final con1 is this, okay. Now we will have activation. So con1 equals to layers dot activation, and we will use ReLU activation. So ReLU and then con1. Okay. Finally, we will be having max pooling layer. So MP1 equals to layers dot max pooling 2D, max pooling 2D, in which we will be passing a 2 cross 2 filter. Okay, with a this is a 2 cross 2 filter with stride of 2. Okay, and then input to this will be con1. So is it understandable to you? Like, are you able to understand this? What I've done? Okay. So this is functional API. Yeah. Thank you so much. Yeah. So this is a very first decoder. Like we can make it a stage decoder stage 1. So this is stage 1 of decoder. Okay. Now we can define like this the stage 2 of decoder. Since we have done max pooling, so the input is downsampled. Okay, so we will, this is stage 2 of decoder. Now we will make it con 2 to max pooling 2. Okay, this is 2 2 2 2. But for this input will be, who will tell me what should be the input to this layer? This is stage of sorry, encoder. Oh, I'm very sorry. Encoder. Yeah. So what will be the input to this? Yeah, exactly. Not con1, but MP1. Yeah, thank you so much. Yeah. So you're getting. So it looks like you are getting too much. Now, here we will take 64 as the filters, number of filters. Okay. Yeah, good. So this is the number of filters that we are having in stage 2. Now we will define stage 3. So we will make a small encoder decoder architecture. So uh, 3-stage encoder and 2-stage decoder. Okay. So this is what we have created. Now there are 128 filters. So 128, 128. This is con 3, 3, 3, 3, max pooling 3. Or because this is last stage, so I'll not take max pooling over here. So I'm commenting this line because we are not taking max pooling, or I'll delete this line so that there's no confusion. So this is max pooling 2. This is convolution 3, 3, 3. So I think you have got this thing. Okay. Now, now we will define decoder. Okay. So decoder starts from here. So first stage of decoder will be what? Upsampling. It will upsample. So what they have done, this encoder, let us first print this, what it has done. So for when we are defining our model using functional API, then you have how we can create the model. So model equals to um, Keras tensor TensorFlow dot Keras dot models, sorry, model, and then inputs inputs. Okay, so inputs equals to this inputs comma output equals to the output. So what is the output right now is convolution 3 right now. It is not fully made, but for temporary we can see that. So con 3, and let us see. batch normalization, layers dot batch normalization, and it is saying batch normalization. Yeah. So it is saying, okay, the correct spelling. Yeah. Again, TensorFlow is not defined. Okay. So import, we have to import TensorFlow. So TF, or we can write import TensorFlow. Sorry, this is Keras. Yeah. So when you will like type model dot summary. So this is the summary of this model. So from 224 cross 224 cross 3, we have reached 56 cross 56 cross 128, because the last layer was having 128 neurons, 128 filters, actually, not neurons, 128 filters. So now when we will add decoder, so this will start again, reshaping to the original input. Like from 56 we will be 112, and then from 112 to 224. Okay. So we will proceed with this thing. Okay. So for upsampling, we can have two options for upsampling. First one is upsampling 2D, and second one is con 2D transpose. So right now we will be using upsampling 2D, because con 2D transpose will, because it learns some filters, so it will take some GPU. So I'll request everyone to make, like, we have to make model light so that it will train in this session only, and then afterwards I'll share one file where you can have con 2D transpose also. I'll let you know how to write con 2D transpose. So first step is we have to upsample. So up1 equals to layers dot upsampling 2D. Okay, so upsampling 2D, we need upsampling 2D. And how we have to upsample it? So we have to give by 2, because we have downsampled it by 2, so we are upsampling it by 2. Okay, and what is the input to this upsampling is convolution 3. Okay, so this is convolution 3 that we are giving it to for upsampling. Okay, now as ma'am had told you, Khanna ma'am had told you today, that there is a unit architecture where we used to share the weights from one layer to another. So suppose this upsampling one output needs weights from this layer to be shared from con2. How to do that? So we'll write merge equals to, this is just a name, so that it can be related. I've used merge because we can relate it to that thing. So merge equal to, we will use layers dot concatenate. Concatenate is the layer. Okay, so concatenate. Okay, layers dot concatenate, and here we will concatenate what? So this is upsampled. Con 3 is upsampled. It means it has reached con 2 size. Okay. So because con 2 was downsampled and given to con 3. So if we have done upsampling to con 3, it has surpassed this thing, and then we can see that it is con 2. Its shape, its size is near to con 2. So how we will do concatenate these two is up 1 comma con 2. This is con 2. Okay. So in this way we have concatenated. So now what we will do after feature sharing, we will perform convolution. So convolution, I'll take this code only to perform convolution. So this is convolution. So I am merging this. Okay. So these two steps, and then convolution. So convolution 4, 4, 4, 4. and this will take the input from merge 1. Okay, so merge 1, then conf 4 4 4. So this is how we have concatenated, and then we have done convolution. Again, conf 4 we will upsample. So I'm again copying this thing. So up one layers dot upsampling 2D, and instead of con 3 we will use con 4. Okay, so this is up 2, and this is merge 2. Now we will add up, sorry, we will concatenate up 2 and con 1 here. Okay, so this is what we have done. Now we can change the filters. So I'll take it like 64 and con 4 is there. Yeah, correct. Now, so now we have reached, if we can see that we have reached, I'm making it sorry, this is con 5. So this is con 5, 5, 5, 5, 5, 5, 5, and this is merged 2 actually. So when I'll again print this model, so I'll take con 5. So let's see what is done. So upsampling 2D, why? Okay, S should be capital. Yeah, upsampling S should be capital. Yeah. So here we have reached to 24, but with how many pixels? 64. So what you can see encoder decoder over here. So it started from 224, then it became 112, just half. Then it became 56. Now after upsampling, it became 56 became 112. Again after upsampling, it became 112 became 224, and now we are having 224. Since we have to generate the mask, so how to generate the mask? Okay, because we need the output as a mask. So concatenate is actually feature sharing. When you will learn UNet, so UNet showed a new concept of feature sharing. Like earlier layers in the UNet, they have something that was very important in the image, and when we were going for downsampling, so some of the features were lost, and because we were doing again upsampling, so without those features which were lost, we were creating our mask. So to make this thing, like to furnish the decoder with important features of encoder of previous layers, we use skip connections. So you can read this UNet paper where you can find what are skip connections. So here there are skip connections. We are sharing the features. Okay, Vishal. So that was your answer. Now we will be having last layer as a mask. So what is the size of mask? Is just 224 cross. Okay, y test, it is saying y test is 288 cross u. So y test we have not. Reshaped. Okay, yeah. So we forgot this line in reshaping this mask. Okay, so I'll reshape this. There was some problem, like we have to check whether the shape is same for x and y, or not. Again, there is some problem. Okay, so we will do that. Like, okay, so I have to figure out whether, because there was here you can see X train was 224, but Y train was 288, 384. So there was some mismatch. That is why I've again done this thing. So now we'll come to this. Now our model is this. This is our model. So it has 786, means 7,86,720 features. Now, since we need a mask, so mask is only 224 cross 224. So now we have to generate the output. So the output will be like a convolution. A convolution, just make like pay attention over here, that convolution 6 equals to, we will be having only one output, so there will be only one feature. Okay, and we will generate this by using one cross one, like point wise convolution, and then we will take con 5 as input, and then we will perform the prediction. So output will be, this will be the output equals to layers dot activation, and this will be sigmoid activation, because there are only two classes, so we are using sigmoid activation, and then this is con 6. So now outputs will be, I'll make it outputs only, so there is no confusion. Outputs equals to outputs. So let us check it out. What is the model summary? So model summary says that there is 224 cross 224 cross 3 as input, and what is the output? Output is 224 cross 224 cross 1. So there will be a single mask, one channel mask. Okay, so this is what we have created as a model. Okay, now we have to compile this model. Okay, so let us compile this model. So from TensorFlow.keras import optimizers, and we will take Adam optimizer. So optimizers dot Adam, and we will set learning rate equals to 0.0001. Okay, so this is the learning rate. Now we will compile this model. So model dot compile. See, so sometimes whatever loss is given in the library, Keras library, sometimes for certain type of problems we have to define our own loss function. So right now I am taking loss function as binary cross entropy loss, because we have taken sigmoid activation at the last layer. So loss, I am defining it as binary cross entropy, but it may happen that our result is not that appropriate that it is acceptable. So we have to define our own loss function. So I'll tell you how to make that. So matrix we need accuracy, but in segmentation problems accuracy doesn't work. Okay, so we have to define like dice loss and all that. What is dice loss or dice coefficient metric? So let us define dice coefficient metric first, so that we will see how our model is learning. So we are defining dice coefficient metric. So dice. So here we will be having one more metric, that is dice coefficient metric. And once we have created dice coefficient metric, we will be having same kind of loss. So every metric takes two things: y predict and y true. Okay. So what is predicted and what is actual? Okay. So y true is what actual, and y pred is what predicted. So there is one operation that we have to cast, because it is something that is actually computed over a tensor. Okay, everything is tensor right now. If we have created a model and then we are doing some computation, then everything is a tensor. So we have to convert this into a tensor. So how we can do that? We have to do all the operations using TensorFlow, because it is a tensor. So y predict is equals to tf.cast. So we are doing casting, so to a tensor. So tf.cast. Now tf.math.greater. I'll tell you what is this. Sorry, tf.math.greater y underscore pred. So everything that is predicted is between 0 and 1. Okay. So we will take anything which is greater than 0.5 as 1, and anything that is less than 0.5 as 0. So tf.math.greater says that in y prediction, in the predicted mass, whatever will be 0.5 or greater will be 1, and whatever is true, actually true, and whatever that is less than 0.5 will be false. So will be 0, will be black pixel. So tf dot float 32. This we have to define. Okay. So and we'll take y true. So y true is, we'll use chars. Okay. So chars dot flatten. So we will flatten that thing, like that array. So underscore y true, and y pred will be k dot flatten y pred. So we have converted y prediction first, then we will compare it with y true. Since y true is having only two values, what are those? 0 and 0.0 and 1. Why? Because we have already converted. It is the label that is stored in y. This y train. So this y train, y test, it is having those values 0 and 1. So whatever our model is predicting, we have to change that also. Okay. So yeah, same for that. Okay. So y pred, and now what is actually dice score? So dice is intersection, twice the intersection over addition of both, like both y pred and y true. So um, I'll tell you later if time permits me. So I'll just write the code. So intersection, we have to find the intersection. Intersection equals to k dot sum. K is chars right over here. So k dot sum y underscore true, comma, sorry, into y underscore pred. So we have to multiply them to find the intersection. So 1 multiplied by 1 will only give 1. So intersection is what is overlapping. So what is overlapping? The ones which are overlapping will give you 1 after multiplying, and every 0 that is multiplied by 1 will be 0. So in this way we will find the intersection. Then return twice the intersection, and to make it like divisibility by 0 and all that, so we will add one epsilon. So this is a very small number. So k dot epsilon, and divide by, now addition of both. So k dot sum y true. So it should be like this. We have to make brackets. So plus k dot sum y predict. Okay. Plus to make it divisibility by 0. So to save it from that condition, so we will add some small number. So k dot epsilon is very 10 to the power minus 6. So it is a very small number. Okay. Now we have to import, because we have used k. So from TensorFlow dot Keras import backend as k. So we have to import the backend. Okay. So let us see uh, unexpected def. Okay, there's some issue with this. Okay, return this. Yeah. So this is our function for dice coefficient metric. So metric we will find it as dice coefficient. Why? Because we are doing some segmentation task on a segmentation problem. So yeah, and later I'll tell you how to define a loss function. So model is being compiled. There is one learning rate. No, no, no. So it is giving me binary cross entropy accuracy. Okay, let me see. Model dot compile and okay, optimizer. Yeah. So model is now compiled. Now we let's train this model. So history equals to model dot fit. We are having training in x equals to x train, comma y equals to y underscore train. Now validation data. Suppose we need validation data. So that is x test, comma y test, and then epochs. So for epochs, we will have some small number of epochs, like 10 epochs. So otherwise, why it is giving me error? So validation data, x test, y test. Okay. So yeah, and then batch size. So batch size equals to, let's take it 8, and validation batch size, let's take it like 4. Okay. And now let's train this model. So positional this y equals to y train. Okay. X train, y train, validation data equals to, okay, validation data equals to, this is equals to, yeah. Let's see what happens. So accuracy, oh, dice coefficient metric is too much. Oh, okay, let it get trained. Then let me check what is. This should be. It is tm.float 32 true dot flat into okay 2 point. Okay, so this model is just trained for 10 epochs. You can see. Let me check again. What is a problem with this thing? Why it is giving me so much, you know, this dice coefficient metric. So we have divided it with yes, y true and y predict and to intersection. I think. Let's do it again. So again, it is giving me so much dice coefficient metric. I don't know why. So I'll take another 5, ma'am. I'll take another 5 minutes. Okay. So this is trained right now. Now let us see what is the prediction. So we'll take it like pred equals to model dot predict, and then we will take y test. Okay, and then batch size equals to 1. So using batch size 1, we are going to predict. Uh, why it is saying this? Oh, sorry, X test. I'm very sorry. This is X test. So on X test, we are predicting. So this spread has the shape 123. So there were, let me tell you. So X test dot. So how many samples were there in X test? 123. Again, what are the samples in YPRED is 123. So because input was 3, output is 1 because it is a mask. Okay. So let us see. I don't know whether it is going to predict very well because we have taken only 20 epochs and our model is not trained very well. So let us see and check. So pred equals to model, sorry. Uh, uh, we will first print the test, like test 0, y test 0. Okay. So what we'll print it. So plt dot im show y test 0. So this was the thing that has to be learned by our model. Then plt dot im show. So this spread 0. So spread 0, comma, all rows, all columns, and 0. Let us see what it has learned. So it was learning. You can see that this because we have not given that much time to train our model. So it was learning something that is, you can see over here. Like this shape, it was learning. So if you will train this model like more than 100 epochs, so it will, I think it will converge to a good good approximation of an input image. So this was the thing that we need to explain you in this session today. Okay. So dice coefficient, I will tell you, dice coefficient is actually this. Um, this is dice coefficient. So 2 into A into B, 2 into A into B divided by A plus B. So what we have taken, this we have taken as the intersection. So when both will have 1 over here, then when they will be multiplied, then only this intersection part will come out. So 2 into this 2.0 into this intersection, we have taken k dot sum y true into y pride. Okay. So this we have taken, and then we have taken intersection over union. So this is A plus B. So that we have taken. So this is y true A and y this y pred B, and 2 into intersection divided by A plus B. So this is 2 into intersection AB divided by A plus B. So that is the dice coefficient that we have taken. So dice coefficient metric will tell you that how much overlapping is there between the predicted mask and the input image, input mask, like true mask. So if the dice score is higher, like 0.9, 0.95, then it is a very good segmentation method that you have like you have tried, you have derived or you have made. So I think I have done. It was so much, today it was so, because of this Google Drive, it has created so much problem. But I think you must have got a small like overview of how you can create this segmentation model. So I'm very sorry from my side that if there is anything that you not understand. So please. Okay, so any latest research trend in image segmentation? Yeah, so there are many models in image segmentation for semantic segmentation, like road segmentation for self-driving cars, and there are semantic segmentation like where are the trees, where is the road, where are the buildings. So this is the thing that we are using. We are going for a research domain. Yes, and there are 2 or 3 things that I haven't told you is actually how to like in while pre-processing the image, there is something that is known as normalizing the image with mean and standard deviation. But there are many things that you can when you are working on a segmentation problem, you have to take care of. So in my case, in WCE images, we have to do a lot of things so that we can improve our dice score and mean IOU. So yeah, thank you very much. Thank you very much everyone for being there.